In the last class, we have discussed in detail about the ionic radius, particularly ionic radius of a cation and ionic radius of a anion, and the variation of the ionic radii as we move from top to bottom in a group, and as we move from left to right in a period in the periodic table. So today I am going to deal with one more important periodic property, that is ionization energy of an atoms and their variation along the group and along the period, and also I am going to give details about the factors controlling or factors affecting the ionization energy. Coming to the ionization energy. Ionization energy is defined as the amount of energy required to remove an electron from a gaseous isolated atom while converting it into its cation is called ionization energy. That is, ionization energy is defined as simply the amount of energy required to remove an electron from a isolated gaseous atom while converting it into its cation. Here, the ionization energy is represented by IE, or it can also be represented by IP. IE means ionization energy and IP means ionization potential. Coming to the what is meant by an ionization energy. The energy required to remove an electron from a gaseous atom or a ion itself is going to be called as an ionization energy. For example, here I have taken an atom, any atom it may be. Particularly, it is better to take the cation having very few electrons in the outermost orbital. The amount of energy required to remove the orbitary electron completely away from the atom. The amount of energy required to remove an electron from the valence shell completely away from an atom. After the removal of an electron from the valence shell, the atom, that is neutral atom, will be converted into a positive ion. So here an amount of energy required to remove the valence electron completely away from the valence shell while converting an atom into a cation is going to be called as ionization energy. The amount of energy required to remove the most loosely bonded electron from an isolated gaseous atom. The amount of energy required to remove the most loosely bonded electron. It means the electron which is revolving in the valence shell is supposed to be most loosely bonded. So, the removal of most loosely bonded electron from an isolated gaseous atom to form a gaseous ion is called ionization enthalpy or ionization energy of that atom. As we know, the amount of energy required to remove an electron is called as ionization energy. If we are going to remove the first electron from the gaseous isolated atom, and this amount of energy is called as first ionization energy and denoted by IE1. It means the amount of energy required to remove the first electron from the isolated gaseous atom is going to be called as first ionization energy, and it is denoted by IE1. Then the amount of energy required to remove the second electron is going to be called as second ionization energy, and the second ionization energy is going to be denoted by IE2. IE2 indicates second ionization energy, that is the amount of energy required to remove the second electron, that is IE2. Then the amount of energy required to remove the third electron is going to be called as third ionization energy and is denoted by IE3. So IE1 is the amount of energy required to remove the first electron from a isolated gaseous atom or a ion. Then IE2 is the second ionization energy which is required to remove the second electron, and IE3 is the third ionization energy. So here, coming to the example of a sodium neutral atom. The sodium atom which is in the neutral condition having 11 electrons. In the valence shell, the sodium is having one electron which is in the form of a 3s1 subshell. If I am going to remove this one electron from the valence shell of a sodium atom, it indicates the removal of one electron. While from the sodium neutral atom, if we have removed one electron from the valence shell while converting the neutral sodium atom into a sodium ion, the amount of energy required to remove one electron or the first electron from the sodium atom is going to be called as IE1. So here, after the removal of one electron, a sodium neutral atom is converted into a sodium cation Na+1. The energy required to remove the second electron is usually higher than the amount of energy required to remove the first electron. And the amount of energy required to remove the third electron is definitely greater than the amount of energy required to remove the second electron. Here, if we remove first electron from an gaseous isolated atom, it forms a cation. If there is a formation of a cation, the net positive charge on the nucleus increases, and this increased nuclear charge attracts the arbitrary electron more and more towards the nucleus. Hence, the removal of second electron becomes higher and higher. So here, the energy required to remove the second electron is definitely higher than the amount of energy required to remove the first electron. Likewise, if we want to remove the third electron from the ion, the nuclear attraction over the arbitrary electron is again increased more and more. The remaining arbitrary electrons are held tightly towards the nucleus. As a result, removal of third electron becomes tougher and tougher. Hence, the amount of energy required to remove the third electron is greater than that of the amount of energy required to remove the second electron. Here, in case of removal of an electron from sodium neutral atom while converting it into a sodium cation, that is, it requires a certain amount of energy to remove the electron. H nu is the amount of energy. It is in the form of a heat energy or in the form of a light energy. When we expose the neutral gaseous sodium atom to a sufficient light energy, or when it is exposed to a sufficient heat energy, the valence electron revolving in the orbitary electron of sodium is going to be completely removed away from the sodium atom. Removal of electron from the sodium atom. For the removal of an electron, the amount of energy whatever required is going to be called as a h nu. It is in the form of a packet of energy or a quantum of energy. H nu is the amount of energy. It is either in the form of a heat energy or in the form of a light energy. If sufficient amount of energy is required to the valence electron, it will be removed completely away. An electron is removed completely away from the neutral atom, and the neutral atom is converting into a cation. Here, after the removal of one electron from a sodium atom, the atom will be converted into a sodium cation. So here, whatever the amount of energy we supply is called as a quantum of energy. The amount of energy required to remove the third electron is higher than that of the amount of energy required to remove the second electron. And again, the amount of energy required to remove the second electron is higher than the amount of energy required to remove the first electron. That is, IE1 is lesser than IE2. Again, IE2 is lesser than I3. It means IE3 is greater than IE2, and again IE2 is greater than IE1. This is because third electron is more tightly shielded than the second electron, and second electron is more tightly shielded than the first electron. Here, the ionization energy is expressed in volts per atom or in kilojoules per mole. 1 electron per atom is equal to 96.4 kilojoules per mole, or simply 23 kilocalories per mole. In general, the value of ionization potential, that is ionization energy, the values of ionization energy increases as we move from left to right in a period in the periodic table. The increase in the ionization energy or ionization potential from left to right in a period in the periodic table is due to the increase in the nuclear charge. As the atomic number increases. The ionization energy values increases as we move from left to right in a period in the periodic table. This is due to the increase in the nuclear charge as the atomic number of an atom increases. The following table indicates the second period of the periodic table. The elements belonging to the second period of the periodic table and their respective ionization energy values in kilojoules per mole. Lithium, its ionization energy is 520 kilojoules per mole. Beryllium, its ionization energy is 899 kilojoules per mole. Boron is 801. Carbon is 1086. The ionization energy value of nitrogen is 1312. That of oxygen is 1482. Fluorine is 1684. While that of the ionization energy of neon is 2081. The values given in the table indicates the first ionization energy of the respective elements. And it is clearly observed that as we move from left to right in a period in the periodic table, particularly here we have taken an example of a second period, that is moving from lithium to neon, there is a constant increase in the ionization energy values is going to be observed. That is, as we move from left to right in a period in the periodic table, the ionization energy values will be increases, and this increase is due to the increase in the nuclear charge as the atomic number increases. And ionization energy goes on decreasing as we move down in the group from top to bottom. This is because of the fact that the increase in the distance of the electron from the nucleus. As we move from top to bottom in a group in the periodic table, the ionization energy values will be goes on decreasing. The decrease in the ionization energy is due to the fact that the increase in the distance of an electron from the nucleus. As the distance increases between the electron and the nucleus, the attraction of the nucleus decreases. As the attraction of the nucleus over the orbitary electron decreases, the electrons are loosely bonded and are very easily removed. For example, the following table indicates as we move from top to bottom in a group, particularly with the alkali metals and their respective ionization energy values. That is, lithium is having the ionization energy of 520 kilojoules per mole. That of sodium is 495 kilojoules per mole. Potassium is having 417 kJ per mole. Likewise, rubidium and cesium. Here, as we move from top to bottom, in a group in the periodic table, from lithium to sodium, sodium to potassium, potassium to rubidium, and from rubidium to cesium. I am here we are going to observe a constant decrease in the ionization energy values of the alkali metals. Lithium 520, sodium 495, potassium 417, rubidium 403, cesium 374 kilojoules per mole. It indicates clearly that as we move from top to bottom in a alkali metals, that is from lithium to cesium, the values of ionization energy will be goes on constantly decreasing. And one more thing, in every group, the inert gases has highest ionization energy and the alkali metals are having lowest ionization energy. Coming to the factors controlling the ionization energy or the factors affecting the ionization energy values. In general, following factors control the ionization energy. Size of the atom controls the ionization energy. Charge on the nucleus, inner shell electrons, completely filled or half filled or empty orbitals also controls the ionization energy. Similarly, the shape of the atomic orbital, either it may be a s orbital, p orbital, d orbital, f orbital. The shape of the atomic orbital also controls the ionization energy values. Coming to the first one, that is size of the atoms. Larger will be the size of the atom, smaller will be the ionization energy. Larger will be the size of the atom, smaller will be the ionization energy. That is, larger distance of the electron from the nucleus weakens the force of attraction and the less will be the amount of energy required to remove the electron. So here the larger will be the size of the atom, smaller will be the ionization energy. Coming to the second factor controlling the ionization energy, that is charge on the nucleus. The charge on the nucleus also affects the ionization energy in the following way. Higher the charge on the nucleus, the greater will be the force of attraction. Higher the charge on the nucleus, greater will be the force of attraction over the electron, and it will becomes more difficult to remove the electron. Hence, higher will be the ionization energy value. Next step. Coming to the one more factor affecting the ionization energy, that is inner shell electron. The electrons in the inner shell produce the screening effect on the nucleus. The electron in the inner shell produce the screening effect on the nucleus. The electrons present in the outer shell are therefore attracted with less force of attraction. Hence, it is easier to remove the valency electron. As it is easier to remove the valency electron, thus larger the number of electrons in the inner shell, less will be the ionization energy value. Coming to the fourth factor which affects the ionization energy or which controls the ionization energy, that is the completely filled atomic orbitals or half filled atomic orbitals or empty orbitals. The atoms having such a type of atomic orbital, either a completely filled or a half filled or a empty orbitals, and the electronic structure in such cases are relatively more stable. Therefore, more energy will be required to remove the electrons. In such cases, the ionization energy will be very high. That is, the half-filled atomic orbitals, completely filled atomic orbitals, and empty orbitals acts as a stable orbital. So it is very difficult to remove the electron from the stable orbital. The orbital having a stable electronic structure are found to be more and more to lose an electron. Hence, in such cases, the ionization energy required will be very high. The last factor, that is the shape of electronic orbitals or atomic orbitals. The shape of atomic orbital also affects the ionization energy. That is, since the s orbital is more closer to the nucleus than the p orbital, as the s orbital is more close to the nucleus than the p orbitals of the same shell, that is easier to remove electron from the p orbital as compared to the s orbital is easier. In general, the ionization energy decreases in the following order, that is, it decreases from s orbital to p orbital to d orbital, and d orbital to f orbital. It means the shape of atomic orbitals or electronic orbitals are also affects the ionization energy values. So today we have discussed in detail about the ionization energy, definition of ionization energy, what is meant of ionization energy, first ionization energy, second ionization energy, third ionization energy, and also we have studied in detail about the variation in the ionization energy as we move from top to bottom in a group. That is, there is a decrease in the ionization energy value as we move from top to bottom in a group, and also we have studied there is a constant increase in the ionization energy values as we move from left to right in a period in the periodic table. And also we have studied in detail about the factors controlling the ionization energy. Mainly, the factors controlling or affecting the ionization energy are the size of the atom, charge on the nucleus, inner shell electrons, completely filled or half filled or empty atomic orbitals, and also shape of the atomic orbitals affect the ionization energy value. And also we have noted that in periodic table the alkali metals are having a lowest ionization energy value, and the values will be goes on decreasing from lithium to cesium. Similarly, the noble gases are having the highest ionization energy values. So this is regarding the today's class, and again in my next class I am going to deal with the one more important periodic property, that is electronegativity of an atom, their increase and their decreases with an example.